Welcome back. In the previous lecture, we had introduced the semi-empirical nuclear mass formula derived via the liquid drop model, and we had shown how it can be utilized for obtaining uh, the mass of any nucleus of a particular Z atomic number and atomic weight A. We will look into few more applications of this formula, and we'll start with how this formula can be utilized to obtain the nuclear radius constant. We'll define what it is, even though we have introduced it in some previous lecture. Let's move on. So we will do this via a mirror nucleus. What is a mirror nucleus? Let's illustrate this with an example. Oxygen with an atomic weight 15, um, it has 8 protons because the atomic number of oxygen is 8. Therefore, O15 would have 7 neutrons. So a mirror nucleus is obtained by replacing all the protons with neutrons and all the neutrons with protons. So if you replace the 7 neutrons via 7 protons, you would get nitrogen. And if you replace the 8, the protons via neutrons, you will get N15. So this has 8 protons, this has 8 neutrons, this has 8 protons, this has 8 neutrons, this has 7 neutrons, this has 7 protons. So these are mirror nuclei of each other. Why do we care about that? Here, the modulus of n minus z is 1 in both these cases. So if you apply the binding energy formula, that is the semi-empirical binding energy formula introduced in the previous lecture, to both these nuclei, and then subtract, you get the difference in binding energy that goes in via this formula. Okay. And if you substituting, simplifying further, you get this particular, here Z minus 1 is 1. Therefore, Z plus N is A. You will get this formula. Therefore, the difference in binding energy can be obtained, can be shown to be this formula. So what is that we know? We also know, just to stop for a moment, we do know, let's say, the atomic mass. Therefore, you can also obtain the difference in binding energy via experiments. And from classical electrostatics, we had mentioned that AC, that is, if you have a uniformly charged sphere, you can obtain the Coulomb interaction for such a sphere. Therefore, from classical electrostatics, you can get AC. Substituting this in the formula mentioned in the previous slide, we get the difference in binding energy to be this quantity. From here, you can get R naught, the expression for R naught. So all the simplifications we obtain via 2 features, right? One is that we have the formula for the mass of any nuclei, and then we have, let's say, delta B from the experiments. So using all these features, this is the nuclear radius constant. You can get the value of nuclear radius constant. Where did we introduce this? We had mentioned in a couple of previous lectures that the radius of the nucleus is related to the nuclear radius constant times a to the 1/3. So if you get R naught via this approach, you can get to the radius of any nucleus using this formula. So in the next lecture, we will look at another application of the semi-empirical mass formula obtained via liquid drop model. We will use that to understand some features of beta decay. Thank you.